Okay, we have function f of xy, our usual function that we've done a lot with, 0.04x squared plus 0.01y squared. The graph of that function being a paraboloid, an elliptical paraboloid. But then we're going to put a 0.1x and a negative 0.1y in there. And we're going to try to determine what the critical points of this function are. Critical points for function of single variable is where the derivative is 0, and that usually gives you a maximum or minimum, but it could give you could get 0 at an inflection point. Okay, so the critical points are the points where the rate of change of the function is 0, and I say, and nothing too weird happens, like something analogous to the inflection point, which is not really weird, but a little bit weirder than a straight concave up or concave down function. Okay, the rates of change in the directions of the coordinate axes are easy to calculate. Partial derivative of f with respect to x and partial derivative of f with respect to y. Now, if these are both 0, then if the function is concave up in both of these directions, then you expect there's a good chance that you have a minimum here. Although it's possible that if you go at the 45-degree direction, function's concave up in the x direction, concave up in the y direction, but at 45 degrees, it's concave down. There's a saddle point. So your rates of change are these. If they're both 0, then you look a little further by checking fxy, the xy partial respect to x, the partial respect to y of the partial respect to x of the partial with respect to y. And if that has a sign that's opposite the signs of the second partials here, it might indicate a saddle point, okay? So that's the process. We start, though, by just calculating the critical points. So the x derivative is this, the y derivative is this. I don't have to read it to you. You've taken those derivatives, and you can see it, and they're very simple. So fx and fy are both 0 at what points? Well, fx is 0 if the sum is 0. That occurs if x is negative 0.1 over 0.08, which is negative 1.25. And fy is 0 if 0.02y equals 0.1, y equals 0.1 over 0.02, which is 5. So your critical point, we got it right away, negative 1.255. Now in general, when you take the x and y partial derivatives, they can be a little more complicated than this. You might not get nice linear equations, and you might have mixed x and y, so you're going to have to solve as simultaneous equations using skills from prerequisite courses. So it's not always as simple as it is here, but this is the process nevertheless. There's your critical point. Now, we look at the second partial derivatives to see if they're both concave in the same direction, at least if we restrict ourselves to an xz plane or restrict ourselves to a yz plane. So fxx is 0.08, fyy is 0.02. They're both positive. Okay? It follows then that the function is concave up in both the x and y directions. I should have maybe said in both the xz and yz planes, or planes parallel to the xz and yz, but that's okay. So we suspect there's a minimum at negative 1.255. Now, why do we suspect a minimum? Because both of these are positive, and positive curvature means you tend to have a minimum. But we have to test for a saddle point. And the test is this discriminant thing here, fxx fyy minus fxy squared. Now think about this for a minute. Well, the test is, as long as this thing is positive, then you have either a relative maximum or relative minimum. If it's 0, you're not sure. And if it's negative, you've got a saddle point. Why is that? Well, first of all, if fxx and fyy are of different signs, this product is going to be negative. Of course, what that means is that one is concave up, and in the other direction you're concave down. So clearly you've got a saddle point, or maybe something worse. Okay? Because if this product is negative, well, this is certainly minus a square is going to be negative, and that ensures that this thing is going to be negative. And that's very consistent with what would happen if we're concave up this way, concave down this way. Well, in this case, both fxx and fyy are positive. We get 0.0016, and fxy is negative. If we take the y derivative, or the x derivative of fy, we get 0. Or if we take the y derivative of fx, we get 0. Okay, well that assures that we have no saddle point, and negative 1.25.5 is a minimum. Okay, well we go on with some other questions. What's the gradient of this function? Gradient's fx times the I vector plus fy times the j vector. There's your fx times I, fy times j. So right there is your gradient. What's the value of the gradient at the point 3, 4? Well, this is a gradient at the point xy, and I think that little thing there looks a lot more like an x than a y. I think it actually was an x. Okay, it's a y. So this is a function of x and y. So we plug the x and y values in for x and y and evaluate it. We get 0.35i minus 0.02j. The question then was, what's the direction of this thing? What's the direction of this gradient at that point? Well, the direction is the arctangent of the y component divided by the x component, the arctangent of negative 0.02 over 0.35, or possibly that plus 180 degrees, but you only add the 180 degrees if the x component is negative, so that's going to be it. Alternatively, it's the direction of the unit vector that you get by dividing this vector by its magnitude. And that comes out, I estimated 0.98i minus 0.06j. I know somebody had 0.98i minus 0.05j. I'm not sure the 0.05, whether it rounded to the 0.06 or stayed at 0.05. But I tend to trust what somebody else got using a calculator to what I got using estimates. And you can kind of sketch the direction of this vector. It's going to be very close to the x-axis because the I component is much greater, 17 times greater than the j component. I use that in making this estimate, so you don't need to worry about it. The maximum rate of increase with respect to distance in the xy plane, if you move in the direction of this unit vector, or at this angle, then your instantaneous rate of change with respect to distance is the gradient evaluated at the point 3, 4. That's the instantaneous rate of change in the direction of maximum increase. Now I say maximum rate of increase, I didn't say it. Maximum rate of increase occurs, it is the magnitude of the gradient, and the direction of greatest increase is the direction of the gradient. Okay, so the maximum magnitude of the rate of increase is this, which is 0.35, might possibly go up to 3.6, but 0.02 is pretty small compared to 3.5. So there we have those results.